Taking a frontier language model, wrapping it in a chat interface, and feeding it a massive prompt creates a fragile illusion of an AI agent. It works in a sandbox, but when deployed into a real environment, it shatters under its own weight. A production-grade agentic AI is a comprehensive software system. It manages state, uses external tools, and triggers real-world APIs to achieve a specific goal over multiple steps. The most common failure mode in early agent design is relying on a single heavy model to handle everything simultaneously. Developers ask one model to classify user intent, extract logic, and execute the final action all at once. This diagram shows a standard mega-prompt architecture. A user input feeds straight into a monolithic frontier model, which tries to write directly to a database. Because a language model is inherently probabilistic, this single-node setup guarantees unpredictable token costs, unacceptable latency spikes, and inevitable reliability failures when interacting with rigid backend systems. An agentic AI is not an autonomous, self-governing entity. It is a deterministic software system, carefully orchestrating a probabilistic and often unreliable core. System designers have to reframe how they view language models. Instead of treating the model as the entire brain of the application, treat it exactly like any other unreliable probabilistic microservice in a backend architecture. This diagram outlines the required target architecture. True control comes from explicitly routing and bounding the model within a multi-node directed acyclic graph, complete with branching logic, isolated storage nodes, and strict gatekeeper checkpoints. We are going to reconstruct this complex graph layer by layer to demonstrate exactly how architectural boundaries prevent catastrophic agent failures. System reliability does not come from waiting for the next generation of foundational models. It comes from engineering strict software boundaries around the models we have today. The first layer of defense in our architecture is model routing. This diagram illustrates how tasks are split. Passing every step through a frontier model creates massive bottlenecks. Instead, low-complexity steps are routed to smaller models. The heavy frontier models are reserved for deep reasoning, synthesis, or highly ambiguous user constraints. Once tasks are routed, we have to enforce how the models communicate. This requires structured outputs. Models cannot return free-form text prose to your backend systems. They must be forced to return predictable, machine-readable structures, using JSON schemas or pydantic models. Routing tasks to specialized models and enforcing rigid output structures cuts latency, reduces token costs, and ensures the output is readable. The second architectural layer manages tools. Tools are the agent's sole interface to the external world, internal databases, and third-party APIs. Tools must act as strict APIs with clear input schemas. A contract barrier rejects malformed requests immediately. A critical principle is isolating low-risk read tools, like gathering availability, from high-risk write tools, like canceling appointments, which require much tighter security. A tool should never accept a vague natural language string like "update this user." A high-risk write tool requires explicit validated parameters, like a user ID, the specific field to update, the new value, and a required confirmation flag. Without these strict tool contracts, an agent operates as a massive security vulnerability, capable of injecting arbitrary, hallucinated commands directly into your backend architecture. The third layer is data storage. A frequent amateur mistake is dumping every piece of context, history, and state into a single vector database. This diagram separates workflow state from semantic memory. State tracks the current execution step and tool calls. Because it dictates the immediate next action, it lives in low-latency databases like Redis. Memory, the broader conversation history, belongs in a separate vector database, pulled only when requested. Stuffing every piece of retrieved memory into a model's context window creates context bloat. The data passed into the prompt for any specific turn must be aggressively minimized to keep the model focused and latency low. Explicitly isolating state from memory is an exercise in data architecture. It prevents the model from hallucinating based on irrelevant past interactions and guarantees the deterministic progression of the current workflow. The final foundational layer is orchestration. Standard application code, not the agent's probabilistic reasoning, must dictate the overarching control flow. Orchestration frameworks provide explicit, codified branching for retries, fallbacks, and handling tool failures. They dictate what happens when a model produces an invalid schema or a query times out. This flowchart demonstrates deterministic validation gates. Consider an appointment cancellation. The language model might correctly classify the intent, but independent code must verify the user's ownership of that record and check business policy rules before the workflow advances to actual execution. Any action that deletes data, issues refunds, or modifies infrastructure demands a human-in-the-loop approval gate. The model suggests the action, the human authorizes it. A safe production agent is entirely subservient to the deterministic business rules codified in this orchestration layer. The software holds the ultimate authority, not the model. When you move to deployment, you realize that traditional software testing assumptions break down. In standard code, if a function runs and no exception is thrown, we assume it worked. In an agentic system, that assumption is invalid. This dashboard illustrates the danger of evaluating only the agent's final text response. A model can generate a polite, perfectly formatted final answer, masking a critical intermediate failure, like pulling the entirely wrong policy document in step 2. This requires trace-level evaluation. Engineering teams must grade every discrete step in the trajectory, from the initial intent classification all the way down to the specific tool argument accuracy. You have to track specialized production metrics to understand system health. That means logging the invalid schema rate, measuring tool call success rates, and calculating the exact cost per successful task. If you cannot observe, trace, and evaluate the exact step where a complex trajectory failed, you do not have a production system. You have an unmaintainable black box. This completed architecture shows how building a reliable AI agent relies on traditional back-end system design, data architecture, and security boundaries. Data flows cleanly through a routing layer, navigates structured tool contracts, utilizes isolated databases, and passes deterministic validation gates. The strict requirements of production software, security, cost efficiency, and reliability are solved by the system you build around the model, not by the model itself. To graduate from fragile demos to robust, real-world software, developers must stop relying on prompt engineering and start engineering the system that controls the prompt.